on everything, and it's not your fault, and everybody's just really just miserable right now. So I'll try and really do a better job of getting more solutions added and clarifying. And yeah, all right. Let's see if this is going. Oh, we are live on live stream. Okay, so um, all right. So I'll add, like I said, I'll add those solutions, and I've got a list here. If we come up with more today, I'll try and get them all done. And I still have some from last time, and it was just totally from laziness, part of depression. I didn't get those FBDs, so we did do them in the video lecture, so I don't feel too bad. But let's go ahead and talk more about chapter 12. And I think last time we left off at 12.8. So today I'll probably start with 12.11. Let's look at 12.11, everybody. All right. (104). All right. So I'll share my screen here. All right. And so it's this one right here, 12.11. All right. So we have this problem here. And just so I can draw the FBD better, I'm going to zoom in a little bit. You know, I like to do that. But so hopefully you have the problem in front of you. You got the wheel of a wheelchair. A person can exert a force tangent to the top of each wheel. There's two wheels in a wheelchair. So there's two forces of F. The radius of the wheel is R. And their center mass is just above this. Determine them. Okay. So this is supposed to be a practical question. The idea is, and this is a calculation that some engineer had to do to figure out the maximum allowable curb height, because there's, you know, if you're trying to make your curbs ADA compliant, we need to make sure someone can actually get over the curb. So this is supposed to be a realistic problem here. And we see that, okay, what if this person has to get over the curb? So I'm going to try and annotate this a little bit. We know that they're going to be pushing here. The picture's terrible, but whatever. We're going to apply a force to the top of the wheel, and that's F, right? Okay, and now there's going to be some weight, and let me get a slightly larger arrow so I can draw that a little better. Let's see. There's going to be the weight acting at the center mass, right? That's going to be mg. All right, sorry, that's a little. And then now comes, this thing is going to lift off the curb, right? So you might, this is something that gets people with this type of problem. So everybody, please pay attention right now. All right. A lot of people, when they're doing this one, they're like, well, it's sitting on the ground. I need a normal force right here, right? Whoops. I wanted to make that a different color. I've got a normal force sitting right here, you might be thinking. However, you don't, because this person is trying to lift off. Now, you're probably okay with there being some force this way, and maybe you're not sure. There's probably some component this way and some component that way at this corner that you're okay with. But I just wanted to point out this force down here should not be there. This is not legit. Why? Because the person is lifting off the curb. As they lift off, that normal force goes to zero. So if they're just barely able to lift off, you could say, another way of thinking about it is they're going to rotate about this pivot point right here. And if they're just barely able to do it, alpha is approximately equal to zero. So you might be saying, wait a minute, this is not a statics problem. You're right, but it's approximately a statics problem if they're just barely able to rotate, okay? So we're going to call it a statics problem to get that limiting value and know that anything above that would cause this thing to rotate, and then it would work. So in the limit where it's just barely, this normal force is approximately zero because it's barely touching anymore or it's lifting off. Any questions about that aspect of this problem? Cool. So let's go ahead and look at the solutions. Whoa, not the solution we're looking for. I think it's a couple more down. All right, so hopefully I have a little bit different coloring there, but it's about the same. So hopefully this makes sense to you. Okay, there's a lot to internalize, blah, 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 blah. Okay, so I just babbled a lot about this crap. So hopefully that's okay. Now, look at this one. This is interesting. Okay, there's going to be friction relative tangent to the curve, and there's going to be a normal force pointing radially inwards. So notice this does look slightly different than the diagram I drew. Remember that if you're dealing with a circular object, it exerts a normal force radially outwards on other objects. By Newton's third law, the curb then must exert a normal force radially inwards. So make sure you're okay with this statement or these green statements. Okay, so take a second to read those. And I'll get this off of here so it's easier to read. Circular object radially outwards. By Newton's third law, normal force radially inwards from the curb. And there's some friction. And now think about this. Maybe if you're wondering how I figured out the direction of friction, I'm trying to rotate this wheel this way, right? So I'm trying to turn the wheel that way. Friction is opposing that relative motion. Think about it. If there was no friction, you wouldn't go upwards. So friction has to be pointing up, right? So the friction is opposing this attempted omega. As you try to rotate downwards, the wheel opposes that and you get friction pushing you up, right? So I should stop there for a sec or get this out. Go ahead and ask any questions you want in the chat. Trey's there again and all that. And then this one is the clever part. Right here, tricky. It asks for the minimum force to get over the curb. So if you ever see a problem like this, you're supposed to know this. That goes to 0. All right. So I'm going to clear that out and scroll down. And notice it's geometry, geometry, geometry. So if you could try and see this triangle right here, hopefully this makes sense. Remember that in this problem, this distance right here was called h in the problem statement. Right? We were told that the curb has height h. All right, so that's why this distance right here is r minus h. And then we were told in the problem somewhere that this distance right here, this distance was 1.2 r in the problem statement. So if you're wondering where I got these dimensions, that's how I got them. Notice I try to do lever arms for this problem. I say the gravitational torque. So clearly I'm saying torques this way are negative. This is a negative torque. Whereas torques this way are going to be a positive torque. And this is my pivot point. That means this causes no torque because line of action runs through pivot. This causes no torque. So because these forces are so tricky to understand, I want to get rid of them, all right? So I put my pivot point right there. All right, and so that's why this, but this reason here is why this is a positive torque. All right, and now that's getting messy, so I can't see everything. Let's go down here and look at the geometry because it's just too complicated up there. So notice in this case, here's mg. This, let me get my pen back. This is r perpendicular for mg, where this is that green pivot point that I'm trying to draw in both pictures right now. So there's my pivot point. There's my pivot point. Because this force is going down, that's where I got this. So I get this ugly looking thing right there. Now this other one look at this crazy one right here. We know that here's my pivot point. Well, in this particular case, because this distance was h, this distance is diameter, or 2r, minus h. And so that's easy to get the lever arm for this force. So again, this force is running perpendicular here. So this is r perpendicular for that force. All right. And let me get an eraser to clean that up a little bit. All right. And I know this is kind of a tough question, so maybe I should pause and see if there's any questions here. Oh, I see. I'm going to scroll down one line here. I see something that's probably worth having on the screen. So here I made a constant right here. So I said K is this, in case you're wondering what this letter K is here. I see I wrote it right below there. That's just that constant. And so you could see here, this is one of the things you got to watch out for. It looks like I've solved for H right there, but notice H is also on this side. So I had to group the like terms. And that's where I got this 1 plus the constant here, right? And so blah, blah, blah. I think this is a good problem for dealing with the geometry. What do you think about that? Is that making some kind of sense? Just give me some kind of feedback, or do you need more time, or is that about right? I'm just checking. Okay, so it looks like that's probably okay for right now on that one. All right, cool. You know, like I said, I appreciate everybody being tough. This is a tough semester, so good job. And I know I'm not doing things as well as I do in lecture, but we're getting something done. All right. Let's take a look at 12.10 because it says it's painful. And so if there's something I can do to reduce your pain now, that's good. So 12.10, same page. All right. And I want to show you some interesting things here. And I want to show you, I think this is why you want to learn lever arms. And I want to show you this one in two ways. So let me get this a little smaller so I can see everything. So we're looking at this one here. Okay. We have a rod of mass M, length L. Oh, and the cable is also length L. So we happen to have an isosceles triangle.
Professor Dorset?
Yes.
You're
Oh,
not
did I forget to
screen
share? Thank you. Thank you. Yep. Sorry, I forgot I stopped the screen share. All right. Sorry. Thank you for catching that right away. Okay. Is that better, everybody? In a second. Yes. Okay. There we go. Okay, cool. Thank you. Sorry about that. And then, yeah, sometimes my chat just disappears randomly here and it takes forever to pop back up. So sorry, I didn't see you say that to me in chat. All right. So we're looking at this problem here. And rather than me try to draw pictures, let's go to the solution right away because I drew a bunch in a bunch of different ways for this one. So this is a really good problem to learn from right now. Okay. So we're trying to do torques and forces. Okay. And I think it's the previous problem. Okay. Okay, so take a look at this one. A clever way to do this problem is shown on the next page. So I just want to show you how nasty this gets. All right. So I spent a lot of time on this one showing you a lot of different ways. So first, hopefully you catch this. I believe this angle was given in the problem statement, and I'm going to confirm that. Yeah, okay, I'm going to assume this is a given. So I'm assuming theta is a given. I should add that into the problem statement. So 12.10 theta is given. Just writing a note. Okay. All right. So if we assume that, you could probably tell this is theta because it's isosceles. And now maybe you saw that this whole thing here is 180 minus 2 theta, right? Because there's 180 degrees in a triangle, and then you could subtract off 2 of the thetas. So, or you could say it's 90 minus theta and 90 minus theta. Another thing you could do is you could say, well, if this angle is theta, this angle must be 90 minus theta. So this angle is back to theta, which tells me that this angle is 90 minus theta. Sorry, that looks sloppy. You can see that this angle right here must be 90 minus. And once you get that, you could do the symmetry here. You could also do this one. You could do all kinds of angles. So look at this weird result here. If you need this angle, we could use that. That might actually be useful right here, right? So in this free body diagram, we get all these complicated ways of doing this thing. And look at this one right here. The forces, when you split them up when your normal XY coordinate system, here's one way to do it. You could talk about the force and the force perpendicular, or you could talk about X and Y and all these angles. It starts to look really crazy and painful. All right. So all there's different ways of doing that one. Now let me show you the next page. If we do this thing with lever arms, maybe you agree this is okay. I don't know. And to be honest, I actually like this way probably the most. So I'm going to get there eventually. This is how you would do that same problem with lever arms. Again, the lever arm is the force distance, or sorry, the distance to the force along the perpendicular bisector. So to make that more visible, here would be the line of action for mg. And notice this distance right here is r perpendicular, because that is the perpendicular distance to the line of action. Now up here, you could see I've already drawn that one. If we know what theta is, you could try and figure this out and you could get it. So I don't really know alpha off the top of my head. Oh, what is this doing here? I don't know what that is. I better clean that up. That was supposed to be inside of here, and it is. So I don't know why that's sitting out there. Writing a note. All right. So that's fine. Now check out this last way down here. So that's a way you could do lever arms. Let me clear all that and scoot down. Look at this one. I think this is actually maybe a little bit easier to understand. So if you look at this FBD, what I did, and maybe not, I have no idea, but I took the tension and I split it into my normal XY, and then I did lever arms for each of those separately. And so when you do that one, if I could write the torque equation for this, I would get, I'm going to write it here. I would get whoops, L cosine. I'm going to use capital Q for theta. I'm using capital Q for theta. That would be a positive torque in this case. And sorry, that's supposed to be red. Let me see if I can fix that. And then I would say, now I don't know if it's going to let me do two colors in the same box. No, it doesn't. Yeah, okay. We'll go back to red. Now I'll do a new text box that's blue. All right. It's killing me. Okay, so now I'll do the blue one. It should be L sine theta times T cosine. Whoops. And then now I do the green one. Negative mg. Gosh, I'm so slow at this online. Oh my gosh. And so it looks a little bit crazy. And you see, we get these double trig formulas. Again, my apologies. That first term should be red. The first term should be red. Oh my gosh. Come on, computer. That term should be red. All right. And so when you do it with lever arms, it just seems a little bit less scary. And then from there, you can kind of work it out. But you do notice you get these cosine sine. So you might have to use a trig formula if you didn't know the angle. So we see that these problems, I just want to point out, depending on which way you do the problem, it looks totally different. And that should be expected. But so this is a good one for trying to do it every single way. Because you can really make sure you understand all this thing. So here was with lever arms. Here was using lever arms on components. And then again, this one up here was using just kind of the classic distance, force, angle between. Distance, force, angle between. Okay. And so you see a lot of different ways to get that. And if you care, you can use this formula to kind of clean things up a little bit. So you could see I did the trig here. I'm going to be honest with you. If I did something this messy, I would probably give you a number for the angle. So if I did this on the final exam, I would probably give you a number for the angle, which would make this dramatically easier because you wouldn't have to keep track of all the 90s and the 180s. You could just get decimal numbers for each angle. Okay. So this is going to be, it's a good problem to practice. It's probably slightly harder than your exam question. I'm gonna pause there. Is that making any sense? That's a nasty looking problem, right? Any questions about that? No, that was just one that I thought was really good to practice because it allows you to see all the different styles that might be useful. I've given exam problems that look like all of these at some point, though. Yeah. Yeah, and everybody, to be honest, you're pretty good at algebra, right? So the most crucial thing in these problems is not solving them. The most crucial thing is making sure you could draw the pictures right, do the geometry. People underestimate doing the geometry. You have to practice geometry in this chapter, and you have to practice writing the force equations, et cetera, et cetera. All right. So, yeah. Should we go ahead and do another one? What do you think? Or am I going too fast if I just jump into another one? Take a look at one more setup. Okay. And I really appreciate your patience. So let's go look at, let's try 12.12. That one is definitely an old exam question. I know. I recognize it because a lot of people missed it. So let's do it. Let's do that one. 12 point, what did I say? 12.12. Sharing screen. And let's go over there, this one. So this is a really good page to make sure. Oh, I love it. I love it. That werewolf. Gotta get that werewolf in there. Okay. This must have been maybe some semester I taught the class near Halloween or something, and maybe the test was near Halloween. It's not that bad. I think the last one was worse. Um, outer radius is R, inner is R over 3. Just going to point something out here. What did it say? Negligible friction between the wall and the spool. So over here, mu equals 0, no friction. Right? We don't have to worry about friction on the wall. And then we do have friction down here. All right, that's cool. Um, Okay, we've got this pulled at some angle. Okay, wires attached to the inner radius. So that's R over 3. And we're going to assume the center mass is right at the center, right? And so now you're pulling it this way, right? Oops, sorry. We're pulling it here with some tension. Then down here, there's a normal force. And now, before we look at the solution, and maybe if you did, it's not a big deal. Try to think, which way is friction pointing at the bottom? And remember, okay, so we're trying to find the minimum tension the werewolf is going to pull to cause the spool to spin. Again, I'm reading the problem right now. It says minimum tension to cause it to spin. All right, if we want it to spin, think which way friction is pointing. Which way, if you pull upwards like that, which way is it going to spin? Clockwise or counterclockwise, and then think which way friction points to oppose that. Okay, so I'm thinking this spool is going to try to spin, looks like, what is that, clockwise. So then I would think there's friction pointing this way. That's what I'm thinking in my mind right now. All right, and I'll check the chat here to see if anybody had something. Okay, yeah, so it looks like that's all good. Now, before we go on here, I see two obvious choices of pivot point. We're trying to figure out the tension. Oops. If we're trying to figure out the tension on 12.12, I want you to humor me. Do you agree this is a terrible choice? This green spot is not a good choice for a pivot point. What force does that eliminate if I put the green pivot point? Tension, correct. And if we eliminate tension, I can't figure out tension. So green is a dumb point. Okay, we do not want to use that. So then there's the red point at the center and the pink point down here, if I can get to my drawing command. So it's either going to be choose this pink point as the pivot or choose this red point as the pivot. Now, you could probably do both of them. You could choose the red point and write a torque equation. You could also choose a pink point and write the torque equation. Now, one of these is a lot easier for dealing with the tension. So let me see. Well, so Jay, if you want, you could unmute and tell me why you think red looks easier.
I just feel like red looks easier because when you look at red, you can find the distance to the tension,
Mm-hmm.
and then you can find that perpendicular line.
Yes.
And then you can also find the perpendicular to the floor as well. And then
Absolutely.
N goes through the
So
pivot. So
I agree with you. Red, it seems automatic for getting that. Now, you could choose the pink, and the problem that Jay is addressing here is how would you get this distance? That's R perpendicular. Now, I do want to point out something. If you choose this pink point, every force except tension drops out, doesn't it? Is that right? Oh, wait, I forgot a force. What force did I forget? Normal force from the wall. So, oh my gosh, that's really going to suck. So the red one is clearly better, right? Yeah, normal force from the wall. Yeah, so take a look. Oh man, this one, so this is a hard one to do. So if you choose the pink pivot point, it's really complicated. If you choose the red one, this is going to get rid of both normal forces, and this is normal force 2, this is normal force 1. It'll get rid of normal force 1, normal force 2, and mg, and leave you only tension and friction. And then you could do a free body diagram and do forces. All right, so let's go look at the solution to this one. Oops, oh crap, I hit the wrong button. Sorry about that. So let's go look at the solution and see how we did this one. Oh, that would have been convenient to use that diagram, right? So here's what I did. I did torques about the center, horizontal forces, and vertical forces. And see if you believe that. Or try to do it yourself without looking at it really quick. I'll give you a minute. See if you could derive those yourself. Okay, I'm going to pause. And you could see my assumptions below here. Get a drink of water real quick. And then I'm going to pause for a second. I just want to see everybody that's in here. Everybody, while you're in here, I mentioned this in office hours, but I know there's more people here now. If you are creative and can come up with alternative styles of assignments for Physics 163, I'm open to thinking about anything. But I do want you to think about the following things. Cost to students, because a lot of students can't afford a lot, and also academic integrity and fairness. Yeah, for Physics 163 in the fall, because we're going to have to be online, I think, again, which is not what anybody wants. It's not what I want. It's not what you want. So, but yeah, that's right now, that's what we've been told we're going to do. So we don't really have a lot of choices for that. Now, if we have to plan for it as if it's going to be that way. So if it's not that way, great. But I have to start planning now for that. And I'm not sure what you mean by a whiteboard. Like you mean behind me, like you have in yours, a dry erase. Yeah, so I can try and get that and see, maybe the school will buy me a whiteboard or something. Yeah, to reduce the lag there or something when you're watching. Yeah. Yeah, that's cool. So what I'm saying is definitely send me an email with anything you can think of. And I just to give you an idea of the kind of challenge that I'm faced with. Obviously, if I want to be fair to everybody, but not have people cheating like crazy, the best way to do it would be to make a different test for every single student. But since it takes me a week to make one test and grade it and write the solutions, or at least several days, it's insane to think of that as a possibility. So remember that whatever suggestion you think of has to be multiplied by 60, right? And so it very quickly makes almost everything unfeasible from a fairness standpoint, from a coding standpoint, or this or that, and like how I coded into Canvas and things. So yeah, if you come up with anything, and so be clever. You could think of totally crazy stuff if it could be scaled up by a factor of 60 for the whole class. Just keep that in mind. I'm open to any thoughts you have. Send me an email. That said, let's get back into this problem and confirm before I get back in there. Yeah, that's it'd be cool. Yeah. I tell you what, Nate Dogg, if you make me an AI that writes the exams, I'll give you an A for Physics 163, or at least consider it. Maybe it's not, I don't know. Yeah, so yeah. It's maybe doable. We'll have to look at that. And I think I just missed a button click there. Where did I miss? All right, where was that? Where'd it go? We could at least talk about it, Nate Dogg, later. Go ahead, Nate Dogg. What?
Oh no, that's Trey. I let Ryan in. I'm able to let people in too.
Oh, okay. Oh, cool. Thanks, Trey. You're faster than I am. That's awesome. Awesome. Yeah, let's make sure we stay on task here and look at this problem. Just let me know. Hopefully this is making some sense here. Okay, that's cool. Okay, yeah. So and Joy in particular, I think on chat you said this problem looks horrible. Do you agree it doesn't seem nearly as bad when you see the result? And Joy, if you could unmute, if that's cool. Is that, what do you think of that? Is that making some sense? Okay, maybe she's doing something. That's cool. And then from there, it's just straight algebra, right? Piece of cake. Oh, I hear you now. What's up?
I know it's Trey again.
Oh,
One thing I wasn't too sure about when I was looking at this picture actually is I wasn't sure if the torque from the string was actually a perfect 90 degrees from the center.
good question. Good comment. Yeah. So to be clear, strings always pull off at a 90-degree angle. And that's a cool thing about these string problems. So in chapter 10, you might remember the string, whether it comes off this way or whatever, it's always going to be at right angles. So these angles are always right angles right here and right here. Is that good, Trey, on that one, would you say, or anything else you'd want to say about that?
Oh, that's good. Yeah.
Yeah, that's definitely worth pointing out. And that's one of the nice reasons you would choose this point at the center, because that gives you this angle. Everything else makes it hard. And notice again, if we do this one's going to have no torque. This one's going to have no torque. This one here, no torque. And that's why only this force and this force, which have simple lever arms, appear right here. And obviously the sine 90 or the lever arm, however you want to think about it. That was good. Other thoughts? Anybody? All right. So let's go ahead and kill that one off. Let's take a look here. I'm going to let you guys try 12.9 on your own. And I want to look at 12.13. I want to look at 12.13. Okay. So 12.13, I'll put it in the chat just in case. So I'll share the screen as well. Let's get to it here. Non-uniform horizontal beam. Position of the center mass is unknown. We do know the left string makes this angle, while the right string makes that angle. Okay. And then call the left end of the beam. All right. So let's see. I'm going to give you a minute for parts A and B. And I don't know if you want to do parts A or B first. I can't remember which one is easier to do first. I just dumped them both in here. Okay. So I'm going to pause for a sec. And I guess to be clear, I'm assuming this is it's supported. When you see supported, that sort of implies static equilibrium. But if you have something like that on the final exam and you're worried, you could always zoom in or email me and ask, and I'll be available. All right. And I'm going to try and maybe make this a little bigger. Just scooting over. All right. And so I'm going to get involved now and do what I would do to think about this. There's a tension this way. Now, if I'm careful with that, I could also draw that as having a component upwards like this and a component this way like that. And now that I've split it into components, I'm going to get rid of the full force vector. So those two are supposed to represent the tension. Somebody tell me something right now. Is this thing moving left or right? What do you think? In static equilibrium, the answer is no, right? Hopefully not. Yeah. Okay. So what does that tell you about the forces in the x direction? They have to be equal, right? So that means this arrow should be about the same size as that arrow. And I'm just going to try and draw it eyeballing it, okay? And now this is how you could figure this out. I know that this tension has to be drawn this way, like that, which tells me, and you could do this in another way if you want, but now I know the vertical component of the tension is like this, right? About there. And so now I know the two tension components. The idea is the left rights have to be the same. So the left rights have to be the same. If the left rights are the same, we could see that this one is going to have a larger vertical component than that one because the angle, right? If they have the same horizontal component, but this one has a bigger vertical because of this angle, we see that the red force has to be bigger. So the left string has more. So I'm going to undo a couple of those things here. So I would say the left string has more tension, and that's how I got there. And now that I see this thing, hopefully you agree, if the left side's supporting more weight than the right side, the center mass is probably on that side as well. So there's mg. And I'll get to the chat. Oh, okay. It sounds like, Nick, you figured it out, hopefully, whatever your question was. All right, cool. Great. That's kind of sneaky, which of course is, chapter 12 is sneaky, people. So I would say it's closer to the left end here. And again, it says it's non-uniform, which that's what tells you it doesn't have to be exactly in the middle. And at first, it probably seemed like it was impossible to determine, but it turns out that's not true either. So hopefully so notice all of this started from getting this component and this component have to be equal. And then from there, you say this one has to have a bigger vertical. And that's what tells you, well, this one's pulling more up. The weight's probably closer to that side. So I'm going to stop there on that. And now it's just same old crap. You do some stuff. We're going to do some torque equation and the force equation. So I would probably maybe I would choose this point and then do the sum of torques, but you could also choose this point where the center mass is, or this point. There's 3 good choices here, and all of them are pretty much equally good. So I would do the 3 forces, and then I would choose one of these pivot points, and then I would do sum of torque about that pivot point, then sum of forces in the X, sum of forces in the Y. Again, just to be clear, maybe if I can get my chat here. Okay, and so that's the strategy, and hopefully you identified that strategy. So even if you miss the conceptual parts there, and look, we've got these angles here. So this is kind of, sometimes I'll do that to speed up the test a little bit. I'll give you an angle so you don't have to write everything in terms of theta. I don't always do that. That last question I didn't. Okay, so all right, let's go ahead and look at it. Oh, whoops. Okay, that's parts B and C of 12.12. By the way, those were extra credit level questions. So if you're wondering about 12.12 B and C and feeling like it's just punishing you, you could probably consider parts B and C as challenge. Okay. All right, let's get to this one. Sorry. Yeah. So challenge. Yeah. Yeah. This tells you where I weigh in on 12.12 B and C. So we're on to that. Yeah. Okay. So there's my picture. Hopefully that makes sense to you. Oh, this is a different way of doing it. Take a look at how I did it here. This is kind of cool. Different way. So I said, well, this is T sine theta. This is T sine phi. And then I'm like, oh, well, if theta's less than phi, that tells me the story. All right. So that's another way to do it. So that's the horizontal force equation. Here's the vertical force equation. And then did I do sum of torques ever? Oh, look at this one. Oh, now I did sum of torques here somewhere. So somewhere eventually I did sum of torques and it works out. So the strategy there is pretty basic. And I'm going to let you work that one out on your own if you want. I'm going to stop the share for a second. So let's see how you're doing. So the strategy that was listed in the chat, pick a pivot, do sum of torques, forces in X and Y. Once you do that, it's just algebra. And that one, you should probably work it out because it's a little bit sneaky. So 12.13, work it out all the way. 12.11, work it out all the way. 12.9 and 10 are good too. So those are kind of as tough as they get. So far, so good. Whew. Everybody, I don't know if I made this clear before, but I think I said this before. We're just going to skip the parts. I'm just going to skip, and that means it's not on the test, and that includes the oral exams. Anything from page 116 all the way back to from 12.19 to the end of the chapter. We'll finish with 12.19. So 12.20. So I'm just not going to test you on it, and I'm not motivated to drag you through it when I know I'm not going to test you on it. It's not that there's not good stuff in there, but if you're a civil engineer, you know, you may want to actually read that stuff after the semester's over. But to be honest, we all need a break and we got to pick something to throw out. So I'm throwing out that and chapter 14. Okay. So, yeah, if I told you that you're supposed to, yes. Yep. Jay, you're correct in the chat. I'm going to look at problem 12.18 right now. That was another really hard one. So I'm trying to look at the nastiest ones in class and just kind of give you an idea how to get them started. And hopefully what will happen is, I mean, let's face it, some of these chapter 12 questions are nasty on the test because my workbook is filled with them from old tests. So let's look at that one. All right. There was something bad about this one for everybody. Oops, am I in the wrong one? That one's a good one here. 12.15 is a classic. Make sure you do that one at home. It's probably been a while since you did a ladder problem. So, ooh, 12.16 is fun. We'll make sure we do that before we quit today. This one. Let me make this a little bit smaller here. All right. So let's take a look at 12.18. All right. A sphere of mass m and radius r supported by this cable on an incline. Assume there's friction between the incline and the sphere is negligible. Okay, got it. Incline angle is alpha. Ooh. The cable connects to the ball such that it exits. Okay, got it. All right. This is another one of those problems where depending on which way you look at it, it could either be easy or torture. And that's what's hard about chapter 12. You actually have to know different techniques and use them and basically think before you choose your pivot point. And now I'm going to blow this up. All right. We got to figure out the angle. All right. So now we're trying to figure out this angle gamma in terms of alpha and beta. So alpha and beta are given. All right, that's fine. So let's see if we can figure out something in here. All right, and so if I draw this triangle, maybe you could see it. And if you don't see that, it takes forever. But this angle up here, whoops, is alpha. And this is a right angle. And once you see that, you're like, oh, that's not too bad. I see that 180 equals 90 plus the angle alpha plus beta plus the angle gamma. And so from there, this drops out. This is going to be 90. And so it's 90 minus alpha plus beta. All right. So hopefully that makes sense. I'm going to assume that part is okay, but this part maybe you didn't see. Notice the trick that I've been trying to emphasize in statics both last time and today is when you see a triangle that's not a right triangle, try to make a right triangle. Like maybe you thought, I'll just go to here. You could do that and it should work out the same way. Maybe you saw it this way and said, oh, this is alpha because of some parallel line theorem. And so this is 180 minus alpha because it's a supplementary angle. And then we, again, still have to use the angles in a triangle sum to 180 here, right? So you could try this way as well. So let me see. Let me check that one. Oh, and maybe it's, so notice in this case, there might be more than one way to describe it. Let me see in this case. So here I would say 180 equals, in this case, what would it be? 180 minus alpha plus beta plus 90. Oh, wait, no, plus gamma, excuse me. And so, yes, Jay, that is, wait, that's Sam. Sam, that is also a correct way of doing it, right? So notice here we get, whoops, I get gamma equals, I bring the other two to the other side. And I get, what is that, beta minus alpha. So that's another good way to do that one. And like I said, we see that there's more than one correct way to do this one, and this is a great way to do it. So other questions on that one? So there's two ways to do it, and those are probably the two that jump out at me. So here we did have to do some extra work. All right. And let's go take a look at the solution and see if there's anything else I had to say about that one. Whoops. What problem is this? 18? So there's a couple different ways you could do that one. So notice there's more than one acceptable answer here for gamma that makes sense. Cool. All right, and then let's go back to the question. So the question for part B is a correct sum of torques equation for the point of contact between the ball and the incline. Sum of torque equals 0 is, oh, so you could tell that was the exam question. So we're asking for sum of torques about this point right here. So I know that there's a normal force here. And let's see, there's gravity going this way. Whoops. Let me make these with arrows so they're a little bit straighter. There's a normal force up this way towards the center. And there's going to be a frictional force this way. And I assume it's pointing that way, and I could be wrong, but we'll worry about that later. There's going to be an MG coming straight down. And then there's this weird tension coming off this way. All right. And so now we have to do a torque equation about this pink pivot point. And there was a chat there, and I'll check. Whoa, that's not what I wanted to do. Fill that in a little bit. Let me check the chat. Oh, friction's negligible. Thank you. Okay, cool. That simplifies my job. So that means I can erase this one. Thank you. Oh, Jay, what was your comment here, Jay? I did it by finding theta as the angle next to beta, and then solved for gamma and subtracted the extra 180.
So when you solve for gamma, I just treated it like two right triangles.
Yeah. And I think what I did, I think I made a typo earlier because this, sorry, let me see if this makes sense. Do you agree that this angle up here is not alpha? This is 90 minus alpha. And I think I wrote it as alpha, didn't I? Yeah, so that should have been, yeah. And so that'll fix it up and make those match it. Okay, so I'm sorry about that, everybody. So that should be 90 minus alpha. And so that will fix up my derivation earlier. I'm totally sorry. I just spaced out there. Yeah, because this is a right triangle here. So that should be 90 minus. And then we would get the same thing. This is alpha right here. And this is alpha right there. Sorry about that, everybody. I just did a bad job. Okay. Jay, are you good with that too? Yep. Okay, cool. Sorry about that, everybody. It's just a screw up. Okay, so this is the normal force. This sucker right here is mg. And this puppy up here is the tension. So now if I choose this pink one, I need to figure out some forces or lever arms, right? And so now we have to do some geometry here. So I guess what I'm wondering here is, what is this angle right here? What is that angle? Well, let's see if we could figure it out. I do know this. You can see it's all geometry. If that is alpha, this should be 90 minus, which means this is alpha, which means this is alpha. Let me do that again with a slightly thinner pen. Again, if this angle here is 90 minus alpha, that makes this angle up here, let's see, this would be 90 minus alpha, right? Because of alternate whatevers, which makes this angle in here alpha again. And then by alternate, this is alpha. So hopefully you see that this angle up here is alpha. By this angle up here, I'm pointing to this one right here, alpha. So I'm going to pause for a second and make sure, is everybody okay how to get this is alpha when I say that? Follow that chain of logic. It's all geometry. Okay. And now we could try to get this, right? We know here, this gets complicated. So you might be saying, oh, maybe I should try and figure out this tension force and try to get the lever arm for that one. So in this case, it's getting kind of messy, and I think I have a good figure already drawn for that one. So I'm going to kind of go over to here and look at it. It's getting kind of sloppy. And so I think this one shows you that picture better. And I'm going to zoom in on this just a second. Ah, what did I just do? All right, I did something stupid there. I don't know what I did. There we go. Got it back. All right, sorry about that, everybody. All right, so take a second and understand this diagram here. So notice we just did the red angles here. So we talked about this one It looks like I did it backwards just so I could fit it in there. So this is 90 minus alpha, and there's another way to get alpha. You can see there's a lot of different ways to do your geometry here. All right, and so now the trick is, how do I get this perpendicular lever arm? And if I show you something, this triangle helps. So I actually used this huge triangle here. I made this right triangle. And so remember, we want the lever arm, which forces this to 90 degrees. And then because I know this angle beta, I'm off to the races here. So in this case, let's see here. This distance here is beta, which makes this angle 90 minus beta. And then this, because this is a right angle here, and I'm getting sloppy, I'm going to clear this out. Because this is a right angle, I know 90 minus beta, and beta sum to 90. So that's why I used R cosine beta. You could also say R sine of 90 minus beta. But remember that trick that we memorized earlier, cosine beta and sine of 90 minus beta are equal. But I just wanted to point out that I had to use this triangle up here. And that was kind of sneaky. Is everybody okay with that? That's a doozy. I actually pulled this problem straight out of Halliday and Resnick and then modified it a little bit. I just took the numbers away. And it turns out when you take the numbers away, people get a lot more lost in the geometry. But I think it's good to force yourself to deal with this type of problem. The rest of it is just a torque equation. R perpendicular times tension, and then R times mg times sine of the angle between. Angle between is alpha that I'm trying to highlight here. So that's where I got this alpha right there. Whew. And you get this really cool result. I think I solved this problem a different way down below as well. Let me see if I could zoom out a little bit. You could do forces, and there's all kinds of stuff. Some people might be wondering, some people did this. Some people wrote this. That was full credit. Some people wrote this. That was full credit. I had to do a lot of work grading this one because I had made such a hard problem. So there were lots of different, these were all different possible correct answers. And it took me a while to figure that out. Those were all different ways that students wrote, and I had to grade correctly. So just know that I'm suffering while I make you suffer when I make these problems tricky like that. Everybody cool with that? I'm sure you're cool with me suffering. Yeah, and so it was kind of fun. I didn't realize it until I started grading it. So I'm like, oh God, this is horrible. So yeah, it's really fun though. Well, I think so. Yeah, I have a strange definition of fun. All right, everybody. How's it? Let me read here. I'm going to stop my video to keep the lag down. Let me see. Sam, can we do it with doing the R perp? When the triangle form a 9. Sam, I don't understand your question. Can you maybe elucidate that for me?
Yeah.
I mean, there's definitely, I will say this, you can do it without R perp for sure. I just don't understand your question.
So should I just share my screen?
Yeah. If that's possible, yeah, for sure. There's so many correct ways to do this one, so I'm not sure. Go ahead and share.
Okay. So that was
12.18. Yep.
So wouldn't this right here make 90 degrees?
Yes.
Okay.
Yes. I tried to say that, but I probably did a bad job. Sorry about that. Yep. One thing I do want to point out, everybody, this is the part that maybe tricks people. You got to be careful here. Actually, I'm going to go to this one. Okay, so I'm going to annotate this and show the tension in green again. And just give me just a second. Here it is. So one thing you got to watch out for is this. If you're trying to do the RF sign of the angle, it gets very tricky because look at this. This is the distance, and you're like, well, maybe you could figure that out. I don't know, but to me, I'd have to think a little bit what that value is, and maybe it's obvious to you. Is it? Maybe you're thinking it's R root 2, but I'm not sure if that's a 45-degree angle or not. It might depend, and maybe it is. I just haven't thought it through. But I still don't know this angle in here, right? I don't know this, but I could figure that out, but it's going to take even more time. So you could call this some distance little r, and then you could call this the tension, and then you could call this angle whatever it is. I'll call it question mark. You'd have to get, it'd be RT sign of that question mark. And that to me is not as obvious as what I had showed you previously. It's not that you couldn't do it that way. It's just that I didn't. And maybe it's straightforward, but we do know that this is R right here. And we know that this is R, but see, I don't necessarily think that's a right triangle. So I don't think it's really obvious to me how to get that. That looks confusing to me. And I'd have to sit there and think it through. Like I said, it probably depends on the parameters. Sam, are you good? Are you good, Sam? Okay, good. I can still, do you care if I mute you? I'm going to do it. And then if I did that, my bad. Sorry about that. Now, everybody, we should probably either take a break or we could do one more problem and call it a day. You want to just take a quick break, or do you want me to push through and then call it? Yeah, let's take a break and we'll come back. All right. Go figure. I tell you what, I'll take a quick break. I'll just make a 5-minute break or something because, yeah, I got to stretch a little bit. I've been sitting in this chair for a couple of hours now. Yeah, so, all right, let's take a quick break and we'll come back. And those of you that wanted to push through, I apologize. I'm going to end the live stream for a minute. All right. Whoops, where is that?